Hello, everyone. It's a pleasure to have you all here. We are living in an era of rapid transformation, and today we're going to look just beyond the horizon of the everyday. We'll dive into how innovations are rewriting the rules and why what seemed impossible yesterday is set to become the industry standard tomorrow. So, settle in. We're ready to begin. This explosive growth brings us to a critical juncture. The battery that powers our devices and cars has remained fundamentally similar for decades. While the cathode has seen significant evolution, the anode, the negative electrode, has remained stubbornly anchored to one material, graphite. Graphite is reliable, but it has hit a physical wall. Its theoretical capacity is limited. To achieve higher energy density, which translates to longer driving ranges and smaller, lighter batteries, we must look beyond graphite. The future of the lithium-ion battery hinges on a new anode material. Today, I will present our work on two promising candidates, silicon-carbon composites and carbon nano-onions, and show you how we are engineering them to overcome their inherent challenges. Before we dive into new materials, let's briefly recall the battery's architecture. A lithium-ion cell is a tightly packed structure. It consists of a cathode, typically a lithium metal oxide, and an anode, which is our focus. Between them lies a porous separator, and the entire system is soaked in an electrolyte. During charging, lithium ions travel from the cathode through the electrolyte and insert themselves into the anode structure. Graphite, with its layered structure, is excellent at this. The ions slip between the layers, causing only a 10% expansion. This process, called intercalation, is highly reversible, which is why graphite anodes can last for hundreds of cycles. A key phenomenon is the formation of the solid electrolyte interface, or SEI. This is a thin, protective layer that forms on the anode during the first charge. It's a necessary evil. It consumes some lithium, causing an initial capacity loss, but it is absolutely critical for stability, as it prevents the electrolyte from continuously decomposing on the anode surface. So why move away from graphite? The answer lies in capacity. Silicon has a theoretical specific capacity of up to 4,200 mAh per gram. That's 10 times higher than graphite's 372 mAh per gram. Imagine a battery with 10 times the energy storage. This makes silicon the primary candidate for next-generation anodes. But there's a problem, and it's a big one. While graphite gently expands, silicon undergoes a violent transformation. When it absorbs lithium, it expands by a staggering 280%, forming a brittle alloy. This massive volume change pulverizes the silicon particles, shatters the delicate SEI layer, and consumes the electrolyte, leading to rapid battery failure. The industry has been forced to either limit silicon content to small fractions or rely on complex, expensive manufacturing techniques. The core challenge, therefore, is to stabilize silicon. One of the most effective strategies is to create a composite by combining silicon with a carbon matrix. Carbon can act as a mechanical buffer and a highly conductive highway for electrons. Our patented method uses pyrolysis to create a core shell structure, what we call silicon-carbon. Here, a silicon nanoparticle forms the core, and it is uniformly coated with a thin, robust shell of carbon, specifically graphene layers. This is not just a simple coating. The carbon shell forms a conformal layer around the silicon core. This architecture does two critical things. First, the carbon shell provides a conductive pathway, overcoming silicon's poor conductivity. And second, it acts as a physical barrier, containing the expansion of the silicon core and shielding it from direct contact with the electrolyte. This preserves the integrity of the SEI layer on the outer shell, preventing it from repeatedly breaking and reforming. Our silicon-carbon powder, with its brownish-black color and 50 to 60 nanometer particle size, consists of a silicon core tightly bound to a graphene-based shell. While silicon offers ultimate capacity, we are also exploring pure carbon alternatives that can offer better stability. Enter carbon nano-onions, or CNOs. These are concentric, spherical layers of graphene, resembling an onion. Their structure is fundamentally different from the flat, layered structure of graphite. CNOs offer unique advantages. Their spherical shape provides a large surface area for electrolyte contact, allowing lithium ions to access the material from any direction, which is great for fast charging. They are highly conductive, and their spherical nanostructure is inherently more stable than flat layers, allowing them to better withstand mechanical stress during lithiation. Our CNOs, produced via a scalable and cost-effective pyrolysis, show a high degree of graphitization with a near-perfect spherical morphology and a particle size of 30 to 60 nanometers. This process is significantly cheaper than methods using nanodiamonds. The true test of any material is in its performance. To evaluate our silicon, carbon, and CNO materials, we assembled them into standard CR2032 coin cells. These were tested against a lithium metal electrode. We developed a rigorous three-stage testing protocol. First, we cycled the cells at a low, slow current to determine their maximum reversible capacity. Next, we tested the materials at different charge and discharge rates. This tells us how well the battery performs under demanding conditions like fast charging. Finally, we subjected the cells to 100 cycles. This is the ultimate test of durability, measuring how much capacity is lost over the lifetime of the electrode. Let's look at the key results. First, the maximum specific capacity. As expected, graphite topped out at 240 milliampere-hours per gram. Our CNO material gave a healthy boost to 300 milliampere-hours per gram. But the silicon-carbon nanocomposite delivered a remarkable 600 milliampere-hours per gram, more than double that of graphite. In terms of coulombic efficiency, all materials performed exceptionally well, hovering around 99%, indicating highly reversible lithium storage. In conclusion, the era of the graphite-only anode is coming to an end. To meet the demands of a rapidly electrifying world, we must transition to high-capacity materials. Silicon holds the key to the next leap in energy density, and through nanoscale engineering like our core shell composites, we are learning to tame its volatile nature. At the same time, materials like carbon nano-onions offer a robust, high-performance alternative for applications where stability and fast charging are paramount. Our journey is about more than just incremental improvements. It's about enabling a future of electric vehicles with longer ranges, portable electronics that last for days, and a more resilient and sustainable energy grid. The next generation of batteries is on the horizon, and it will be built on innovative materials like these. Thank you for your attention. Stay with me.